Hi everyone. In this lesson, the last lesson in differentiation, we're going to have a look at differentiation from first principles. So right at the start of this differentiation topic, I showed you the formula for actually working out how to differentiate something. The question is though, why does that formula work? Why does that give us the gradient of a curve at the point we're interested in? Well, that's what we're going to have a look at in this lesson. So this is what we're going to cover. If we remember, differentiation is all about finding the gradient of a curve. So we're going to go back to basics and look at how we find the gradient, and we're going to build that up to the general formula for differentiation. This is a very complex topic, very, very difficult, okay? So you will need to bear with me a bit and you might need to repeat this video a couple of times, but really try and pay attention and see if you can understand what's going on. We'll have a look at a few examples as well, and as always, we'll finish off with an exam style question. Okay, so how do we find the gradient of a curve? Well, if we remember the gradient, which we call m quite often from y equals mx plus c, it's the change in y over the change in x. Okay, that's how we figure out the gradient. If we look at a graph, it's the change in the y coordinate over the change in the x coordinate is how steep that curve is. Okay, so let's take an example. Say we want to find the gradient of y equals x squared at the point x equals 2. So let's get a graph to see what's going on. Here's our graph of y equals x squared. Here's x equals 2 down here. Say we want to find the gradient at this point. How could we do that? First things first, we already know the answer to this by knowing how to differentiate. So if we differentiate y equals x squared, remember multiply by the power, take one off the power, dy by dx equals 2x. So at x equals 2, the gradient is 4. So just so we know where we're going with this, here's the actual answer of what the gradient is. But if we didn't know the formula for differentiation, how would we do that? How would we estimate it? Okay, let's draw a line between 2 and 3. Okay, so it's a straight line, so it doesn't quite follow the curve between 2 and 3. And let's put some markers on for where that goes. So x equals 2, y equals 4, yeah, because it's a graph of x squared. And x equals 3, y equals 9. And let's mark on delta x and delta y and think about how big these are. Okay, so basically I've just drawn a triangle here and we're saying, okay, we want to approximate the gradient at x equals 2, so I'm going to look at this straight line between x's 2 and 3. Delta x is between 2 and 3, right? So it's going to be 1. And delta y goes from 4 to 9, so it's going to be 5. So the gradient is delta y over delta x, so it's 9 minus 4, which is 5, over 3 minus 2, which is 1. That's the change in the x coordinate. And 9 minus 4 was the change in y coordinate. That gives us a gradient of 5. Okay, it's pretty close. We know it should be 4, so it's pretty close. Why isn't it working exactly? Well, we wanted the gradient at 2. Actually, what we've worked out is kind of like the average gradient between 2 and 3. You can see by the fact that this green line doesn't exactly follow the red curve that it's just an estimation, because we've assumed this curve is a straight line in that region. It's not really. So we found a slightly higher gradient than what it actually should be. How could we get a better estimate? Okay, let's get rid of that and try this instead. We're going to now look at between 2 and 2.5. Instead of going all the way from 2 to 3, we'll only go from 2 to 2.5. You can see this pretty closely follows the curve, so this should be a pretty good estimate. Let's put some markers on again. So at 2, y equals 4. At 2.5, you'll actually find y is 6.25 if you square 2.5. So our delta x and our delta y are marked on again. Remember, delta x is just the change in the x coordinate, delta y the change in the y coordinate. Change in the x is 0.5 here, from 2 to 2.5, and the change in the y goes from 4 to 6.25, so it's 2.25. So we can work out the gradient again. Do delta y over delta x, gives us 2.25 on the top, over 0.5 on the bottom, which gives us a gradient of 4.5. We're getting pretty close to the gradient we know it should be, which is 4, but we're still not quite there, okay? But it got more accurate when we took a straight line from 2 to 3, and then we went from 2 to 2.5. It got more accurate, didn't it? So maybe we could do like a line between 2 and 2.1, and then it would be even more accurate, and then 2 and 2.01, it would be even more accurate. And if we got it down to 2 and 2.0000001, we'd probably have pretty much exactly the right gradient. So what I'm going to do now is I'm going to take a more general example. Here's our y equals x squared graph again. I've got rid of the axes for a second. Okay, here's our line again. This is our estimate of the gradient at a point. There's the top line, there's the bottom line. Now let's say, instead of saying it's at x equals 2, let's just keep it really general and say it's just at the point x. That means the y-axis is going to be x squared. And now, instead of saying it's 2.5 or whatever, let's say it's just x plus h, where h is a little bit. So we've got x and a little bit more, so x plus h. That means on the y-axis, since it's the graph of y equals x squared, it's going to be x plus h squared. H is just a number we're using to keep it really, really general. Okay, so instead of going from 2 to 3 and then 2 to 2.5, we're saying we're going from x to x plus h. Okay, and we can make h whatever we want, but we'll keep it really general for the moment. So we've got our delta x and our delta y. If we have a look, our delta x goes from x to x plus h, so the difference is h to go from one to the other. Our delta y is going to be x plus h squared, this point, minus x squared. Okay, so it's going to be that point minus that point to get the change in y. So how do we get the gradient? The gradient is delta y over delta x. Okay, the change in y is x plus h squared minus x squared, what we've got here, and the change in x is this x plus h minus x, which just simplifies down to be h. What I've also done here is multiplied out this x plus h squared. Remember that x plus h squared, we can just write that in two brackets like this. And it's going to give us x squared plus 2xh plus h squared. So it's just multiplying out double brackets there. Now have a look at this. Can you see we've got an x squared and a minus x squared? They're going to cancel each other out. So actually, we can just write it as 2xh plus h squared, okay, because those x squareds cancel each other out, and we've still got the h on the bottom. Now what we can do is we can cancel that h. We can say h over h there, and h squared over h just leaves us an h. Okay, so I'm saying cancel this bit and cancel the squared there. We're just left with 2x plus h. Okay, now let's say we want h to be as small as possible. Do you remember when we did our example before, we did between 2 and 3, that was okay. 2 and 2.5 was better, so if we could do 2 to 2.1, that'd be really good. 2 to 2.01 would be great, and so on and so on. So basically, if we let our h get really, really small, so it's kind of like 2 to whatever, 2.00001, then we're going to get a really good estimate. So this line here means h is approaching 0. So that line means approaches. Why can't it be exactly 0? The reason it can't be exactly 0 is because of this h here. See, it's on the bottom of a fraction. If we have h equals 0 on the bottom of a fraction, we get into all sorts of problems, okay? So it has to be just very nearly 0, not exactly 0. But if we do that, our gradient is going to be 2x, isn't it? It's going to be 2x plus something very, very close to 0. So our gradient is given by 2x. Okay. Now, do you remember, if we differentiate y equals x squared, we get dy by dx equals, multiplied by the power, it's 2. Take 1 off the power, 2x. You see how it matches up? We haven't actually used the standard differentiation formula. We've just used our knowledge of the gradient, and we get exactly the same answer. That is actually how it works. Okay, that is using this method is how we actually differentiate everything, and it's just an easier formula we apply to get this method here. But that is kind of first principles. So if you see a question asking from first principles, this is the kind of thing they want you to do. Okay, so this was specifically for the graph of y equals x squared. What we're going to do now is we're going to look at a completely general graph. It's not y equals x squared, it's just y equals some function of x. It can be anything you like, it's just y equals f of x, where f of x tells us whatever the function is. It's some very weird function here, maybe a cubic or something like that. Right. So we're going to pick a random point, and we're going to say we're after the gradient here. Draw my green line on. Put some markers on. Right, now, this first line, we're going to say this is at x. Now, the equivalent y coordinate, it says y equals f of x, so the y coordinate is going to be f of x, okay? Where f of x is whatever our function was. So before, f of x was y equals x squared, so f of x would just be x squared here, okay? At this point, we're going to do x plus h again. So this is going to be f of x plus h, because that's our x coordinate, not x anymore, but x plus h. Okay, so this is just as general as we can possibly make it. If you're still following, you're doing really, really well, because this is very tricky. Just try and stay with me on this bit, and I'll show you the general formula in a second. Okay, so we need our delta x and our delta y again to work out the gradient. So the delta x goes from here to here, and the delta y goes from here to here. Okay, so how can we write that? Well, the gradient is delta y over delta x, and we said delta y is this one, f of x plus h, minus f of x to give us this distance here. Yes, that's what's on the top line of this fraction. The bottom line is delta x, which is x plus h, minus the x here to give us this distance, delta x. Okay. Now, x plus h minus x is just h. Okay, and this is basically the most general formula we could have. I'm going to do one extra thing. I'm going to say, to make this differentiation, or this estimate of the gradient even, as good as possible, I want to make this h really, really small, so I'm taking the gradient really precisely. Remember back to our first example when we saw taking it between 2 and 3 was okay. 2 and 2.5 was better. 2 and 2.1 would be even better. So we want h to be really small. So I'm going to write this, which looks really complicated, but it's not too bad really. This here means limit. What I'm saying is, I want this equation in the limit that h approaches 0. Okay, that sounds really complicated, but all we mean is we're going to take this expression, and I want to know what the answer is when h is really, really small. Okay, and this is actually the general formula. So that formula we just had is the general formula for differentiation. That's actually how we differentiate anything. Okay, is with this formula. You can differentiate absolutely anything with this formula. And the other formula we use is really just a shortcut of this one. It's just but we need to be able to do it from first principles as well, which is why I'm showing you this formula. If you get a question that says differentiate this from first principles, you have to use this formula. And remember, this means the limit as h gets very close to 0. Okay. So basically what it means is we're going to set h to 0, and we've simplified it.